At the smallest scales of the universe, far below anything that can be seen or touched, modern experiments have revealed something quietly unsettling. Pairs of particles behaving as though separation were incomplete, properties appearing linked even when distance intervenes, outcomes lining up with a precision that seems to ignore where or how far apart those particles happen to be. Not as a rare anomaly, not as an error, but as a repeatable feature of nature itself. Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these slower explorations, and if you feel like it, share where in the world you're listening from tonight. It's always grounding to know how widely these quiet ideas travel. For more than a century, physicists have been probing the foundations of reality, using instruments designed to isolate the smallest interactions imaginable. From tabletop experiments carried out in darkened laboratories to international collaborations spanning continents, carefully prepared systems have revealed correlations that persist no matter how thoroughly the components are separated. Measurements made here are reflected there, not after a delay, not through any detectable signal, simply as part of a shared description that refuses to break apart. According to everyday experience, objects influence one another through contact, forces, or signals that move through space. Yet these quantum experiments suggest that, at a fundamental level, nature does not always divide itself along such familiar lines. What appears separate may still belong to a single, extended whole. This strange behavior did not arrive as a dramatic discovery, but as a quiet consequence of the maths describing quantum systems. It raised questions not only about particles and measurements, but about how information, causality, and physical reality itself are organized beneath the surface of experience. Institutions across the world continue to refine these tests, closing experimental gaps and improving precision, not to amplify mystery, but to understand it carefully. With each refinement, the results remain consistent. The connections persist. The correlations hold. Tonight's journey explores that subtle connection, not as a paradox to be solved, but as a feature to be understood slowly, a phenomenon that challenges intuition without threatening order, one that asks not for belief, but for patience. Quantum entanglement does not suggest that the universe is chaotic or unknowable. It suggests something quieter, that nature may be more deeply coordinated than everyday experience prepares us to expect. Settle in. Let the connections reveal themselves gently. Quantum entanglement belongs to a part of physics that deals with the smallest building blocks of nature, a domain where familiar rules quietly stop applying. In everyday life, objects behave as individuals. A cup can be lifted without moving the table. A light can be switched on in one room without affecting another. Space, distance, and separation feel absolute. Classical physics was built to describe this world, a world where causes precede effects, where influences travel gradually, and where objects carry their own properties wherever they go. Quantum mechanics describes a very different layer of reality. It does not replace classical physics so much as sit beneath it, governing behavior at scales far smaller than atoms, where particles like electrons, photons, and quarks dominate. At this level, nature does not present itself as a collection of independent objects moving through space like tiny billiard balls. Instead, it behaves more like a set of relationships, patterns, and probabilities that only settle into definite outcomes when measured. Quantum entanglement emerges naturally within this framework. It is not an exotic add-on or a special trick of the theory. It appears whenever quantum systems interact in certain ways and then separate again. Once formed, entangled systems are described together, even when the particles involved move far apart. The maths of quantum mechanics does not assign each particle its own fully independent description. Instead, it assigns a single shared description to the system as a whole. This is one of the first places where everyday intuition begins to struggle. In ordinary experience, separation feels final. Two objects pulled apart become two things. In quantum physics, interaction can leave a lasting imprint. Particles that have shared a common origin or exchanged energy can remain linked in their behavior, even after distance grows between them. That link is not a force pulling them together, and it does not involve signals travelling back and forth. It is a consequence of how the system is defined at a fundamental level. To understand why this happens, it helps to step back into the early years of the 20th century, when physicists were trying to make sense of experimental results that refused to fit classical explanations. Phenomena such as black body radiation, the photoelectric effect, and atomic spectra revealed that energy did not always behave smoothly. Instead, it arrived in discrete amounts, later called quanta. This shift forced scientists to rethink what physical properties meant and how they were assigned. In classical physics, properties like position, momentum, and energy are assumed to exist whether or not anyone measures them. Quantum mechanics challenged this assumption. It introduced a description in which certain properties do not have definite values until an observation takes place. Before measurement, the theory describes a range of possible outcomes, each with a certain likelihood. This does not mean particles are vague or unreal. It means their behavior is governed by rules that differ from macroscopic expectations. When two quantum systems interact, their possible outcomes can become linked. The combined system must be described together, not as two separate lists of properties, but as a single structure containing correlations. These correlations are the heart of entanglement. They specify how the outcome of one measurement relates to the outcome of another, without assigning independent values in advance. An important point is that entanglement does not violate the speed limit set by the universe. No information is sent faster than light. Experiments conducted by research groups across the world, including those associated with major universities and national laboratories, consistently show that while outcomes are correlated, they cannot be used to transmit messages instantaneously. What changes is not what one particle does to another, but how their behaviors are statistically related. This distinction matters because it separates entanglement from science fiction imagery. There is no hidden signal racing across space, no invisible thread pulling outcomes into line. The connection exists in the shared description of the system itself, once the system is prepared in an entangled state. The correlations are built in from the start. Distance doesn't weaken them because distance is not what created them in the first place. Early quantum pioneers were unsettled by this implication. Physics had long relied on the idea that systems could be fully described by listing their parts. Entanglement suggested that, at a fundamental level, the whole could carry information that the parts alone did not possess. This was not a philosophical preference, but a mathematical requirement of the theory that successfully explained experiments. Over time, this framework proved extraordinarily reliable. Quantum mechanics underpins technologies used every day, from semiconductors and lasers to magnetic resonance imaging, better known as MRI. Entanglement, as a feature of that same framework, inherited this credibility. It remained strange, but it was not optional. Wherever quantum systems interacted and separated, entanglement appeared in the equations and later in experiments. Another reason entanglement feels disorienting is that it challenges the habit of thinking in terms of objects with fixed identities. In quantum physics, what matters is often how systems relate rather than what they are in isolation. Properties can belong to pairs or groups instead of individuals. This is not how tables, planets, or living organisms behave, but it is how nature behaves at its most fundamental scale. This chapter establishes that entanglement is not a mystery floating outside physics. It is rooted deeply in quantum mechanics, a theory developed to explain real observations and tested with extraordinary precision. The difficulty lies not in the theory's accuracy, but in the mismatch between quantum behavior and the expectations built from everyday experience. By placing entanglement firmly within its scientific context, it becomes easier to approach it without distortion. It is neither magical nor arbitrary. It is a consequence of a framework that describes how microscopic systems share information, energy, and history. Once that framework is in place, the idea that particles can remain correlated across distance no longer appears as a violation of nature, but as an invitation to rethink what separation really means. From this foundation, attention can now narrow. Having established where entanglement lives within physics, the focus can move from the broad structure of quantum mechanics to the specific kinds of relationships that make entanglement one of the most carefully studied and quietly profound features of the modern scientific view of reality. When physicists say that two particles are entangled, they're not describing a physical knot, a signal, or a mysterious force tying objects together across space. They're describing a very specific kind of relationship, a relationship so tight that the system must be treated as a single whole, even when its parts are no longer close to one another. In everyday language, it feels natural to talk about objects as separate things. A coin on a table has its own properties. Another coin in a pocket has its own properties. Each can be described independently, without reference to the other. Classical physics is built around this assumption. Systems are understood by breaking them into parts, describing each part, and then adding the pieces together. Quantum entanglement breaks that habit in a subtle but fundamental way. When two quantum systems interact under the right conditions, their properties can no longer be described independently. Instead of assigning each particle its own complete set of attributes, quantum mechanics assigns a shared description to the pair. The system becomes one combined entity, even if the particles later move far apart. This does not mean the particles lose their individuality in every sense. Each can still be detected in a specific place. Each can still be measured. What changes is how their measurable properties relate to one another. The outcomes are linked. Knowing something about one immediately tells something about the other, not because information has travelled between them, but because the system was defined that way from the moment it was created. A simple way to think about this is through paired properties. Imagine two objects prepared so that they always give opposite results when tested, but neither result is fixed in advance. If one shows one outcome, the other must show the opposite. Before measurement, neither outcome is settled. After measurement, both are. The important point is not which result appears, but that the relationship between them is perfectly preserved. In classical thinking, this would suggest that each object carried hidden instructions all along, waiting to be revealed. Quantum mechanics does not support that idea. Instead, it describes the pair as sharing a joint state that only resolves into definite outcomes when a measurement takes place. The relationship exists first. The individual results come later. This is where many misunderstandings begin. It is tempting to imagine that when one particle is measured, it sends a signal to the other, telling it what to do. Experiments have repeatedly ruled this out. No measurable signal travels between entangled particles at the moment of measurement. Nothing moves through space to enforce the correlation. In fact, the results remain correlated even when the measurements are arranged so that no signal travelling at the speed of light could possibly connect them in time. Because of this, physicists are careful with their language. Entanglement does not involve communication. It does not involve control. It does not allow messages to be sent. It describes correlations that are built into the system as a whole. The outcomes line up because the system was prepared that way, not because one part reacts to the other. This distinction matters because it keeps entanglement grounded in testable science rather than drifting into metaphor. Research groups around the world, working in universities and national laboratories, routinely create entangled systems using photons, electrons, and even small groups of atoms. The behavior observed in these experiments matches the predictions of quantum mechanics with remarkable consistency. The correlations appear exactly as described, and no additional mechanisms are required to explain them. The idea that a system can only be fully described as a whole is one of the deepest shifts introduced by quantum theory. It asks for a different way of thinking about physical properties. Instead of belonging to objects in isolation, some properties belong to relationships. They describe how parts of a system fit together, not what each part is doing on its own. This is not entirely foreign to everyday experience. A single musical note means little on its own, but relationships between notes create harmony. A sentence is not defined by individual letters, but by how those letters are arranged. In these cases, meaning emerges from structure rather than from isolated pieces. Quantum entanglement is similar, but it operates at a level where intuition is less forgiving. The term entanglement itself was introduced by Erwin Schrödinger in the early 20th century, as he grappled with the implications of the theory he helped build. He recognized that this feature was not a side effect, but a central aspect of quantum mechanics. In his view, it was the characteristic trait that separated quantum physics from all classical descriptions of nature. Understanding entanglement as a description of relationships rather than communication helps clarify why it feels so strange. Classical physics trains the mind to expect that influence requires interaction through space. Quantum mechanics suggests that some correlations do not arise from influence at all, but from shared origins and shared descriptions. The universe, at its smallest scales, keeps track of connections in a way that does not rely on continuous exchange. This also explains why entanglement challenges classical assumptions so deeply. Classical thinking assumes that objects carry their properties with them, fully formed and independent. Entanglement shows that, under certain conditions, properties are not owned individually. They are distributed across systems. What exists is not a list of attributes, but a pattern of possibilities. Physicists do not treat this as a philosophical curiosity. They treat it as a practical feature of the theory, one that must be accounted for in experiments and applications. Entire fields, such as quantum information science, are built on the careful use of entangled systems, precisely because these correlations are robust, predictable, and deeply rooted in the structure of quantum mechanics. By defining entanglement in this way, as a shared description, rather than a hidden message, it becomes easier to see why it has held up under decades of scrutiny. It does not ask for new forces or unseen signals. It asks for a shift in how systems are described at the most fundamental level. With this definition in place, the strangeness of entanglement becomes more manageable. It is no longer a story about particles whispering across space, but about how nature organizes information when systems interact. That realization opens the door to a deeper question. If these relationships are built into the theory itself, how did physicists first recognize them, and why did they cause so much unease when they were first brought into the open? In the earliest days of quantum theory, entanglement was not introduced as a bold new idea or a deliberate proposal. It appeared quietly, almost accidentally, as a consequence of equations that otherwise seemed to work astonishingly well. Physicists were not searching for strange connections across space. They were trying to explain stubborn experimental results that classical physics could not accommodate. At the beginning of the 20th century, The microscopic world was already proving troublesome. Experiments involving light and matter revealed behavior that refused to fit established rules. Energy arrived in discrete amounts. Electrons behaved as both particles and waves. Measurements produced results that could only be predicted statistically. To make sense of this, physicists developed mathematical tools that described systems not by fixed trajectories, but by evolving probability structures. These mathematical descriptions were powerful. They predicted experimental outcomes with remarkable accuracy, but they also carried implications that were easy to overlook at first. When two quantum systems interacted and then separated, the equations did not always allow each system to be described on its own. Instead, the maths insisted on treating them together as a single combined object, even after distance grew between them. This was not initially recognized as a problem. Early practitioners were focused on calculation and prediction. If the equations worked, they were used. Only later did physicists begin to ask what these descriptions implied about the nature of reality itself. When they did, the implications were unsettling. One of the first to articulate this discomfort was Albert Einstein. Although he played a central role in shaping quantum theory, he remained deeply uneasy about its implications. He believed that a complete physical theory should describe reality as it exists independently of observation. The idea that properties might not have definite values until measured conflicted with his sense of how nature ought to behave. Erwin Schrödinger shared this unease, even as he contributed decisively to the theory's development. He recognized that the mathematical structure of quantum mechanics allowed systems to become inseparably linked. It was Schrödinger who later gave this phenomenon its name, not as a celebration but as a warning. He viewed entanglement as the feature that most sharply distinguished quantum mechanics from all classical descriptions. Niels Bohr, by contrast, took a different view. He argued that quantum mechanics did not need to provide a picture of underlying reality in classical terms. For Bohr, the theory was complete, as long as it correctly predicted the outcomes of experiments. Questions about what particles were doing when unobserved, he suggested, might simply be the wrong questions to ask. These differing perspectives gave rise to early debates about completeness and realism. Was quantum mechanics a full description of nature, or was it an incomplete approximation pointing toward a deeper theory? Did physical properties exist prior to measurement, or were they created by the act of observation? Entanglement sat at the center of these questions, because it made the issue impossible to ignore. The maths was clear. When systems were entangled, no description assigning independent properties to each part could reproduce the predictions of the theory. Any attempt to do so required additional assumptions, often involving unseen variables or hidden instructions carried by the particles. These ideas were attractive to those who wanted to preserve a classical picture of reality, but they were not part of the original theory. What made entanglement especially troubling was that it seemed to conflict with deeply held assumptions about locality. In classical physics, influences travel through space over time. Objects can only affect one another through direct contact or through fields that propagate at finite speeds. Entangled systems, by contrast, exhibited correlations that did not weaken with distance. The relationship appeared to persist no matter how far apart the components became. It is important to note that this was not a claim about faster-than-light influence. Early quantum theorists were careful to distinguish correlation from causation. Still, the fact that the theory linked outcomes across distance without any mediating process felt deeply uncomfortable. Even those who accepted the mathematical formalism found the implications difficult to reconcile with intuition. This discomfort was widespread. It was not limited to a single school of thought or a single personality. Many physicists regarded entanglement as an indication that something essential was missing from the theory. Perhaps quantum mechanics was a statistical approximation, incomplete in the same way thermodynamics is incomplete without reference to molecular motion. Perhaps a deeper layer of reality existed beneath the formalism, waiting to be uncovered. For a time, these concerns remained largely philosophical. The practical success of quantum mechanics overshadowed its conceptual difficulties. The theory worked too well to discard, and the strange correlations it predicted were not yet experimentally accessible in a decisive way. Entanglement remained a theoretical curiosity, noted in the equations but rarely tested directly. Still, the unease lingered. As experiments improved and techniques became more refined, physicists began to realize that these questions could not be postponed indefinitely. If entanglement was a real feature of nature, it should be possible to test its implications. If hidden explanations existed, they should leave detectable traces. The stage was quietly being set for a more formal challenge. The early clues had accumulated, the maths had spoken clearly, the debates about realism and completeness had sharpened. What remained was to find a way to turn philosophical discomfort into experimental confrontation. Entanglement, which had emerged unintentionally from the structure of quantum theory, was no longer just a mathematical oddity. It had become a fault line running through the foundations of physics, marking a place where intuition, theory, and reality appeared to pull in different directions. By the early 1930s, unease about quantum mechanics had settled into a persistent background hum. The theory worked extraordinarily well, yet its implications refused to sit comfortably with long-held ideas about how the world ought to behave. It was in this context that Albert Einstein, together with Boris Podolsky and Nathan Rosen, set out to sharpen the problem rather than ignore it. Their aim was not to overthrow quantum mechanics, nor to challenge the accuracy of its predictions. In fact, they accepted its experimental success. What concerned them was whether the theory could be considered complete. In other words, did quantum mechanics describe all elements of physical reality, or was it a partial account pointing towards something deeper? To make this question precise, they introduced what later became known as the Einstein-Podolsky-Rosen argument. It was framed as a thought experiment, not as a proposal for a laboratory setup. The purpose was conceptual clarity. By imagining a carefully prepared pair of particles and reasoning through the consequences of quantum mechanics, they hoped to reveal whether the theory left something essential unexplained. At the heart of their argument lay two assumptions that felt almost self-evident to many physicists at the time. The first was realism. This is the idea that physical properties exist whether or not they are observed. A particle has a position, a momentum, and other attributes as part of its objective state, not because someone happens to measure them. The second assumption was locality. According to locality, influences do not act instantaneously across distance. What happens here should not immediately affect something far away without some mediating process travelling through space. Taken together, these assumptions form what is often called local realism. They were not invented by Einstein and his colleagues. They were inherited from centuries of classical physics and everyday experience. Objects have properties. Causes precede effects. Signals take time to travel. Nothing about these ideas seemed controversial. The thought experiment imagined a pair of particles created together in such a way that their properties were tightly correlated. Quantum mechanics predicted that measuring one particle would immediately allow a prediction about the other, even if the particles were far apart. This was not a speculative claim. It followed directly from the mathematical structure of the theory. Einstein and his colleagues asked a careful question. If the result of a measurement on one particle allows a definite prediction about the other, and if no influence can travel between them instantaneously, then the second particle must already possess the corresponding property. Otherwise, how could the prediction be reliable? In their reasoning, this implied that quantum mechanics was not accounting for all elements of reality. Something was missing from the description. This line of reasoning did not accuse quantum mechanics of being wrong. Instead, it accused the theory of being incomplete. The equations delivered correct predictions, but perhaps they did so by averaging over deeper variables that remained hidden. In this view, the strange correlations associated with entanglement were not fundamental. They were symptoms of an underlying structure not yet captured by the theory. It is important to emphasize what the argument did not claim. It did not propose a specific alternative theory. It did not introduce new forces or mechanisms. It did not suggest that experiments were flawed. It was a challenge aimed squarely at interpretation. Either quantum mechanics was incomplete, or one of the assumptions of local realism had to be abandoned. This was where the tension lay. Giving up completeness would mean accepting that the theory was provisional, awaiting a deeper explanation. Giving up realism would mean accepting that physical properties do not exist independently of observation. Giving up locality would mean accepting that nature allows correlations that defy classical notions of separation. None of these options felt comfortable. Niels Bohr responded by rejecting the premise of the argument rather than its logic. He argued that the very demand for hidden elements of reality was misplaced. According to Bohr, quantum mechanics did not describe an underlying reality in classical terms, and it was a mistake to expect it to do so. Measurement, in his view, was not a passive revelation of pre-existing properties, but an active process that defined what could meaningfully be said about a system. This disagreement was not about calculation. Both sides could use the same equations and arrive at the same experimental predictions. It was about what those equations were taken to represent. Einstein wanted a theory that described the world as it exists independently. Bohr was content with a theory that described the outcomes of experiments without committing to a deeper picture. The Einstein-Podolsky-Rosen argument crystallized this divide. It made the tension explicit and unavoidable. For the first time, entanglement was not just a curious feature of the maths, but a central player in a foundational dispute. The argument showed that quantum mechanics forced a choice. One could not keep all the intuitions inherited from classical physics and also accept the theory as complete. Despite its significance, the argument remained largely philosophical for many years. At the time it was proposed, there was no practical way to test its implications directly. The correlations it discussed were subtle, and the experimental control required to probe them lay beyond available technology. As a result, the debate simmered rather than exploded. Still, the question posed by Einstein, Podolsky and Rosen did not fade away. It lingered in the background of physics, resurfacing whenever discussions turned to the meaning of quantum theory. Was the world fundamentally probabilistic, or merely appearing so because of incomplete knowledge? Did distance truly limit influence, or was that assumption an artifact of classical thinking? What made the argument enduring was its clarity. It reduced a vague unease into a sharp dilemma. Either quantum mechanics was incomplete, or the structure of reality was stranger than previously imagined. The argument did not demand an immediate answer, but it made clear that an answer would eventually be required. As experimental techniques improved and new generations of physicists revisited these questions, the Einstein-Podolsky-Rosen argument took on a new role. What had begun as a conceptual challenge became a guidepost, pointing towards specific features of the theory that could, in principle, be tested. The problem was no longer whether quantum mechanics made strange claims, but whether those claims could be confronted by observation. In this way, the argument quietly transformed the discussion. It shifted attention from abstract debate to the possibility of experimental resolution. The discomfort it exposed did not undermine physics. Instead, it sharpened it, setting the stage for a deeper examination of how nature handles correlation, separation, and reality itself. For many physicists, the strange implications of entanglement felt less like a revelation and more like a warning sign. Quantum mechanics produced astonishingly accurate predictions, yet it seemed to do so by abandoning ideas that had long provided comfort and clarity. Properties appeared unsettled until measured. Correlations appeared without visible mechanisms. For those raised on the orderly logic of classical physics, this felt unfinished rather than profound. Hidden variable theories emerged from that unease. They were not fringe ideas or acts of rebellion. They were careful attempts to restore a sense of completeness to quantum theory. The basic idea was simple. Perhaps the uncertainty described by quantum mechanics did not reflect the true state of nature, but rather a lack of information. Maybe particles carried additional properties, hidden from current measurement, that determined outcomes all along. In this view, quantum mechanics was not wrong. It was incomplete. Much like thermodynamics describes heat and pressure without tracking every molecule, quantum theory might describe averages while concealing deeper details. The randomness it predicted would then be apparent rather than fundamental. Probability would reflect ignorance, not indeterminacy. This possibility was deeply appealing. It preserved determinism, the idea that physical processes unfold according to definite rules. It also preserved locality, the expectation that influences do not leap across space instantaneously. Together, these ideas formed a worldview that felt intellectually stable. Nature might be complex, but it would remain orderly beneath the surface. Albert Einstein was among those who found this perspective compelling. His discomfort with quantum indeterminacy was well known. He accepted probability as a useful tool, but not as a final description of reality. To him, a complete theory should specify what exists, not merely what can be predicted. Hidden variables offered a way to reconcile quantum success with classical expectations. Other physicists explored similar ideas for similar reasons. They were not necessarily committed to any specific hidden mechanism. What they shared was a desire for explanatory closure. They wanted a theory that told a clear story about what particles were doing, whether or not anyone was watching. However, as these ideas developed, an important distinction became clear. Not all explanations are equally testable. A theory can be logically appealing and still remain beyond experimental reach. Some hidden variable proposals were so flexible that they could reproduce any possible outcome. While this made them difficult to falsify, it also weakened their scientific value. Physics does not judge theories solely by how satisfying they feel. It judges them by what they forbid. A strong theory does not just explain what happens, it rules out what cannot happen. This is where many hidden variable ideas began to struggle. Without clear constraints, they risk becoming philosophical positions rather than physical theories. There was also a practical challenge. Any hidden variables would have to reproduce all the successful predictions of quantum mechanics. That included not only simple experiments, but a vast range of results accumulated over decades. The bar was high. Any deeper theory would need to match quantum mechanics where it worked, while also explaining why entanglement appeared to violate classical expectations. As research continued, it became increasingly clear that the issue was not merely whether hidden variables could exist, but whether they could coexist with the assumptions physicists were trying to preserve. Could a theory be both deterministic and local while still matching quantum predictions? Or did entanglement force a deeper compromise? This question sharpened the debate. It shifted attention away from vague dissatisfaction and toward precise conditions. If hidden variables existed, what properties must they have? What limits would they impose on observable correlations, and most importantly, could those limits be tested? Gradually, physicists began to realize that this was not just a philosophical puzzle. It was a mathematical one. The structure of correlations predicted by quantum mechanics was not arbitrary. It followed specific patterns. If hidden variables were responsible, they would have to reproduce those patterns while respecting locality. This insight changed the tone of the discussion. Instead of asking whether quantum mechanics felt complete, physicists began asking what any alternative theory would be forced to obey. The focus moved from interpretation to constraint. What kinds of correlations are possible in a world governed by local hidden variables? And how do those compare with what quantum mechanics predicts? Once framed this way, the problem became sharper and more hopeful. If the predictions differed, then experiments could decide between them. The search for certainty no longer depended on metaphysical preference. It depended on measurable outcomes. Hidden variable theories had served an important role. They clarified what physicists wanted to preserve and why. They exposed the assumptions lying beneath familiar intuitions, and by doing so, they helped define the precise questions that needed answering. The stage was now set for a decisive development. The issue was no longer whether quantum mechanics felt unsettling, but whether its predictions could be distinguished from those of any theory that clung to classical ideas of locality and determinism. What was needed was a clear mathematical boundary, a line that no local hidden variable theory could cross. Once such a boundary was identified, the debate would shift again. The question would no longer be which explanation felt more reasonable, but which description nature itself followed. By the early 1960s, the discussion surrounding quantum entanglement had settled into an uncomfortable pause. Quantum mechanics continued to succeed with astonishing reliability, predicting experimental outcomes across atomic physics, chemistry, and emerging technologies. Yet the unease it generated had not diminished. Physicists were no longer questioning whether the theory worked. They were questioning what kind of world could possibly behave in the way the theory described. At the centre of this tension sat a persistent hope. Perhaps quantum mechanics was not the final word. Perhaps a deeper description existed beneath it, one that restored familiar ideas about cause, locality, and certainty. Hidden variable theories kept that hope alive, but they suffered from a critical weakness. No one could say with precision what such theories must predict differently from quantum mechanics itself. That changed with the work of John Bell. Bell approached the problem with unusual clarity. Rather than asking which interpretation of quantum mechanics felt most reasonable, he asked a sharper question. If a theory relies on hidden variables and insists that influences do not travel instantaneously across space, what limits does that impose on observable behavior? If those limits could be identified, then nature itself could be asked to choose. This was the breakthrough. Bell realized that local hidden variable theories are not infinitely flexible. They cannot reproduce every possible pattern of correlation. Instead, they are constrained by the assumptions they preserve. Bell showed that these constraints could be expressed as precise limits on how strongly separated systems could be correlated. This result became known as Bell's inequality. Despite the name, Bell's inequality is not a single formula to be memorized. It is a family of related conditions that apply to a wide class of experiments. At its core, it draws a boundary. If measurement outcomes obey that boundary, then local hidden variables remain viable. If the boundary is crossed, then at least one classical assumption must be abandoned. What made this development extraordinary was that it did not depend on interpretation. Bell did not argue for or against realism, determinism, or any philosophical position. He simply asked what follows if certain assumptions are true. If hidden variables exist and if locality holds, then correlations must remain below a specific threshold. That conclusion is unavoidable. Quantum mechanics predict something very different. Under carefully prepared conditions, entangled systems should display correlations that exceed Bell's limit. These predictions are not exotic additions to the theory. They arise naturally from the same structure that explains atomic energy levels and chemical bonds. If quantum mechanics is correct, violations of Bell's inequality are not rare exceptions, they are expected. This was the turning point. Before Bell, debates about entanglement could drift endlessly. One could always argue that quantum mechanics was incomplete in principle, even if no one could say how. After Bell, that position became testable. Either the correlations observed in nature respect the limits imposed by local hidden variables, or they do not. Bell was careful to emphasize what his result did not imply. A violation of the inequality would not mean that information travels faster than light. It would not imply that one measurement causes another at a distance. The distinction between correlation and communication remains essential. Even in quantum mechanics, outcomes cannot be controlled to send messages instantaneously. What Bell demonstrated was subtler and more disruptive. He showed that correlations can exist which cannot be explained by local causes acting independently on each system. The universe, at a fundamental level, may not be reducible to separately specified parts whose behavior is fixed in advance. This insight reframed the entire discussion. The problem was no longer about philosophical discomfort. It became a question of constraint. What kinds of explanations are compatible with observed correlations? Which assumptions survive contact with data? At the time Bell published his work, its importance was not immediately recognized. The experiments required to test the inequality demanded extraordinary control over measurement settings, timing, and separation. In the 1960s, such experiments were difficult, expensive, and technically uncertain. Many physicists regarded Bell's work as elegant but impractical, a beautiful argument awaiting a future generation. Yet the idea did not fade. Quietly, it changed how physicists thought about entanglement. Bell had transformed a vague conceptual worry into a concrete experimental challenge. He had given the field a measuring stick. This shift had a profound effect on the culture of quantum foundations. Questions that once sounded abstract became operational. How far apart must systems be to rule out ordinary communication? How rapidly must measurement choices be made? How can unwanted correlations introduced by the environment be eliminated? These were no longer philosophical puzzles. They were engineering problems. Bell's inequality also clarified what was truly at stake. If experiments violated the inequality, then the classical picture of the world as a collection of independently defined objects would be incomplete. Reality would not be fully describable by listing properties carried by each part. Relationships themselves would play a fundamental role. Importantly, Bell did not claim that quantum mechanics provided a complete picture of reality in any ultimate sense. He resisted oversimplified conclusions. His work did not dictate which interpretation of quantum mechanics must be adopted. It merely ruled out a large class of alternatives that attempted to preserve both locality and hidden determinism. This distinction is often missed. Bell did not settle the meaning of quantum mechanics. He narrowed the space of possible meanings. He showed that any future theory must confront entanglement directly, rather than explaining it away. Over time, advances in experimental techniques made Bell's proposal increasingly practical. Improvements in optical sources allowed physicists to reliably create pairs of entangled photons. Faster electronics enabled rapid changes in measurement settings. More precise clocks reduced ambiguity about timing. What once seemed unreachable began to look feasible. As interest grew, laboratories around the world began preparing experiments designed specifically to test Bell's inequality. The goal was no longer to debate whether quantum mechanics felt strange. The goal was to see which correlations nature actually produced. Bell's contribution reshaped the study of quantum physics in a quiet but lasting way. He showed that even the deepest questions about reality could be addressed with experimental care. Philosophy did not disappear, but it was anchored to measurement. By identifying a boundary that classical assumptions could not cross, Bell gave physicists a way forward. The abstract became tangible. Theoretical unease became an experimental program. Entanglement, once a troubling feature of equations, became a phenomenon that could be tested, measured, and quantified. The groundwork was now firmly in place. The inequality had drawn a line between competing explanations of the world. What remained was to confront that line with reality itself, using carefully designed experiments capable of revealing whether nature respects classical limits or follows the more deeply connected structure predicted by quantum theory. Testing quantum entanglement in the laboratory requires turning an abstract idea into something that can be prepared, measured, and repeated with care. For physicists, this meant finding physical systems that could reliably exhibit entanglement and designing experiments precise enough to distinguish genuine quantum correlations from ordinary coincidences. One of the most commonly used systems involves particles of light, known as photons. Photons are convenient because they can be created in pairs, guided along different paths, and measured with great accuracy. In many experiments, a single physical process produces two photons at the same moment, with their properties linked from the start. These properties might include polarization, which describes the orientation of the light's oscillation as it travels. When two photons are entangled in this way, their polarizations are not fixed independently. Instead, they are described together. Measuring the polarization of one photon immediately constrains what will be observed for the other, even if the photons are sent in opposite directions. Importantly, the individual outcomes remain unpredictable. Only the relationship between them is fixed. Other experiments use particles such as electrons or atoms, focusing on properties like spin. Spin is often described as a kind of intrinsic rotation, though it does not correspond to literal spinning in space. What matters experimentally is that spin measurements can yield discrete outcomes, commonly described as up or down relative to a chosen direction. Entangled particles can be prepared so that their spin outcomes are tightly correlated when measured along the same axis. Creating entanglement is only the first step. The real challenge lies in measuring it convincingly. Quantum correlations are subtle, and ordinary experimental noise can easily obscure or mimic them. This is why experimental design matters so deeply in this field. One crucial requirement is isolation. Entangled systems must be shielded from unwanted interactions with their environment. Stray electromagnetic fields, thermal vibrations, or unintended collisions can disrupt the delicate quantum state, a process known as decoherence. When decoherence occurs, the system loses its entangled character and begins to behave more classically. Preventing this requires careful control over temperature, shielding, and timing. Another requirement is precise timing. In many experiments, measurements on entangled particles are performed at locations separated by significant distances. The timing of these measurements must be controlled so that no ordinary signal could travel between them in the available time. This ensures that the observed correlations cannot be explained by slower, classical influences. Experimental setups often include fast, randomly chosen measurement settings. Instead of fixing how each particle will be measured in advance, the choice is made at the last possible moment. This prevents any hidden coordination based on prior knowledge. The goal is not to trick nature, but to rule out alternative explanations that rely on prearranged instructions. Landmark experiments began to appear in the late 20th century, building gradually on one another. Early tests demonstrated correlations consistent with entanglement, but left room for doubt due to technical limitations. As methods improved, later experiments closed these gaps one by one. Detectors became more efficient, distances increased, timing precision improved. What made these efforts convincing was not a single dramatic result, but consistency across many independent experiments. Different research groups, using different particles, different distances and different techniques observe the same patterns. The correlations predicted by quantum mechanics appeared reliably, regardless of the specific experimental details. Repeatability is central to scientific confidence, and entanglement experiments have been repeated countless times. Results obtained in one laboratory have been reproduced in others, often with increasing sophistication. Experiments have been performed across rooms, across buildings, and even between ground stations and satellites. Each time, when the conditions are right, the correlations persist. Careful statistical analysis plays a major role in these studies. Individual measurements are not meaningful on their own. What matters is the pattern that emerges across many trials. By collecting large data sets and comparing them to theoretical predictions, physicists can distinguish genuine quantum correlations from random fluctuations. Independent verification has been especially important given the foundational nature of the questions involved. Because entanglement challenges classical intuitions, claims about it demand exceptional scrutiny. Experiments are designed not only to confirm quantum predictions, but to actively search for flaws. Controls are built in to test whether mundane effects could account for the observations. Over time, the picture has become remarkably clear. Whenever experiments are performed with sufficient care, the results align with quantum mechanics. Correlations exceed what any local hidden variable explanation would allow. This agreement holds across different physical systems and measurement strategies. It is also worth noting that these experiments do not depend on exotic conditions. While they require precision, they rely on well-understood physical principles and technologies. Lasers, detectors, optical fibers, and electronic timing systems all play familiar roles. The strangeness lies not in the apparatus, but in what the apparatus reveals. As techniques advanced, researchers began exploring more complex forms of entanglement, involving more than two particles or more intricate relationships. These experiments further confirmed that entanglement is not a fragile anomaly, but a robust feature of quantum systems when prepared appropriately. Despite the consistency of results, physicists remain cautious. Every experiment is designed with the assumption that errors are possible. Alternative explanations are considered and tested. New experiments aim to close remaining loopholes and refine measurements even further. This ongoing scrutiny reflects confidence in the method, not doubt in the outcome. What emerges from this body of work is not a single decisive moment, but a gradual accumulation of evidence. Entanglement is not supported by one clever setup or one fortunate measurement. It is supported by decades of careful experimentation carried out by independent teams around the world. These laboratory tests transformed entanglement from a theoretical curiosity into an empirical fact. They showed that the strange correlations predicted by quantum mechanics are not artifacts of maths, but features of the physical world that can be observed and quantified. At the same time, the experiments clarified important limits. They confirmed that entanglement does not allow control over individual outcomes. No matter how carefully the system is prepared, measurements retain an element of unpredictability. The correlations are real, but they cannot be used to send messages or manipulate distant systems at will. This balance is one of the most striking aspects of entanglement experiments. They reveal connections that defy classical explanation, while preserving the broader structure of physical law. Causality remains intact. The speed of light remains a fundamental limit. What changes is how correlations are understood. By grounding entanglement in repeatable laboratory tests, physicists shifted the discussion from speculation to observation. The question was no longer whether such correlations were conceivable, but what they implied about the structure of reality. With experimental evidence firmly in place, attention naturally turns to interpretation. What does it mean for nature to behave this way? How should these results be understood within the broader framework of physics? The laboratory has spoken clearly. The remaining task is to make sense of what it has revealed. When experiments violate Bell's inequality, they do not announce a revolution with flashing lights. They deliver something quieter and far more disciplined. They tell physicists that certain ways of explaining the world no longer work. Not because those explanations are unpopular or unfashionable, but because nature itself refuses to behave according to their rules. To understand what these results actually show, it helps to begin with what Bell's inequality represents. It is not a prediction of quantum mechanics. It is a limit derived from a particular class of explanations, specifically those that assume hidden variables and locality. If the world were governed by such mechanisms, then correlations between separated systems would always remain below a certain threshold. That threshold is not negotiable. It follows directly from the assumptions. When experiments consistently exceed that limit, they do not prove that quantum mechanics is philosophically correct. They demonstrate something more precise. They rule out the entire family of explanations that rely on local hidden variables. Whatever the correct description of nature may be, it cannot belong to that class. This distinction matters because it keeps conclusions grounded. Experimental violations of Bell's inequality do not tell physicists what reality ultimately is. They tell physicists what reality cannot be. That may sound modest, but in science it is a powerful form of knowledge. Over decades of experimentation, violations of Bell's inequality have been observed under increasingly strict conditions. Different particles have been used, different distances have been tested. Measurement choices have been varied rapidly and unpredictably. Each time the same pattern emerges. The correlations predicted by quantum mechanics appear, and the limits imposed by local hidden variable theories are exceeded. What these results rule out is the idea that particles carry pre-existing instructions that determine measurement outcomes independently of one another, while also respecting locality. No matter how cleverly such instructions are imagined, they cannot reproduce the observed correlations. This is not a failure of imagination. It is a mathematical impossibility confirmed by experiment. Importantly, these violations do not imply that influences travel faster than light. This is one of the most persistent misunderstandings surrounding entanglement. Experiments show strong correlations, but they do not show controllable effects. The outcome of any individual measurement remains unpredictable. Observers cannot choose the result they obtain, and therefore cannot use entanglement to send messages. This limitation has been tested as carefully as the correlations themselves. Physicists have arranged experiments so that measurement choices are made randomly, at the last possible moment, and in ways that cannot be anticipated by the systems being measured. Even under these conditions, the correlations persist, but no usable signal appears. The universe remains stubbornly respectful of its speed limit. In this sense, experimental results reinforce an important boundary. Entanglement challenges classical explanations of correlation, but it does not undermine causality. Effects still follow causes. Information still travels through space at finite speeds. What changes is not how signals move, but how relationships are structured. Another point often overlooked is how conservative the conclusions actually are. Violating Bell's inequality does not force physicists to adopt any particular interpretation of quantum mechanics. It does not mandate one worldview over another. Multiple interpretations remain consistent with the same experimental facts. What the experiments do is constrain them all. Any interpretation that survives must accommodate non-classical correlations. It must accept that systems cannot always be described as collections of independently specified parts. Beyond that, interpretations may differ in how they describe measurement, probability, or reality itself. The experiments do not choose among these options, they simply narrow the field. This emphasis on constraint rather than proclamation is a hallmark of careful science. Physicists are not in the business of declaring metaphysical truths based on a single set of results. They are in the business of mapping which explanations remain viable as evidence accumulates. The precision of modern experiments has reinforced this approach. Statistical uncertainties are analysed carefully. Sources of noise are identified and controlled. Data is compared across independent laboratories. The consistency of results matters more than their drama. In fact, one of the striking features of entanglement experiments is how ordinary the equipment often appears. Lasers, detectors, optical fibers, and electronic timing devices are familiar tools. There is no mysterious apparatus. The strangeness lies entirely in the correlations revealed, not in the machinery used to reveal them. This grounded character is important because it keeps discussion anchored to physics rather than speculation. The experiments do not invite mystical interpretations, they invite careful accounting. What assumptions went into this explanation? Which of those assumptions are incompatible with the data? By answering those questions, physicists have learned something surprisingly robust. Nature permits correlations that cannot be reduced to local causes acting independently. At the same time, nature does not permit those correlations to be harnessed for communication or control. The balance is precise. Connecting these experimental facts back to theory reveals why quantum mechanics remains so resilient. The same mathematical structure that predicts entanglement also predicts its limits. Quantum theory does not allow arbitrary correlations. It predicts specific patterns that fall between classical constraints and unrestricted randomness. Experiments land exactly where the theory says they should. This agreement is not superficial. It extends across different formulations of the theory and across different physical systems. Whether working with photons, atoms, or other quantum objects, the same relationships appear. The theory does not need to be adjusted or rescued. It already contains the behavior observed. What the experiments actually show, then, is not chaos or contradiction. They show coherence. A set of predictions derived from a particular theoretical framework matches reality with remarkable consistency, while alternative frameworks fail in specific, identifiable ways. It is also worth noting how patient this process has been. No single experiment settled the matter. Each result added weight. Each improvement reduced ambiguity. Over time, confidence grew not because physicists wanted a particular outcome, but because repeated tests converged on the same conclusion. This patience reflects the culture of the field. Foundational questions demand exceptional care. Claims are scrutinized. Loopholes are discussed openly. New experiments are designed to address remaining doubts. The aim is not to win an argument, but to understand what nature permits. By now, the pattern is clear. Bell inequality violations are not anomalies. They are expected outcomes of quantum theory, confirmed repeatedly by observation. They rule out a specific class of explanations while leaving others open. This is why physicists speak cautiously about what the experiments prove. They do not prove that reality is non-local in a simplistic sense. They do not prove that observation creates reality. They prove something narrower and more durable. Certain classical assumptions cannot all be true at once. The result is a landscape shaped by limits. Some paths are closed, others remain open. Understanding entanglement requires navigating that landscape without overstepping what the evidence supports. With the experimental facts firmly established, attention naturally shifts toward how these results should be understood, not in terms of spectacle or paradox, but in terms of interpretation. If nature allows correlations of this kind while preserving causal structure, what does that say about how physical systems are described? The experiments have done their part. They have spoken with clarity and restraint. What remains is the quieter task of interpretation, where theory, philosophy, and physics meet, guided not by wonder alone, but by the firm boundaries drawn by evidence. Once experiments established that entanglement is a real and repeatable feature of the physical world, a new kind of question came into focus. The question was no longer whether quantum mechanics worked, or whether entanglement existed. Those issues had been settled by evidence. The remaining question was how this behaviour should be understood. This is where interpretations enter the picture. An interpretation of quantum mechanics is not a competing theory with different predictions. It does not change experimental outcomes or alter the maths used in calculations. Instead, it offers a way of thinking about what the theory says the world is like beneath the surface of measurements. In the case of entanglement, interpretations attempt to explain what it means for systems to share correlations that cannot be reduced to independent properties. One of the most widely discussed perspectives is often associated with the view that quantum mechanics does not describe an underlying reality in the classical sense at all. In this approach, the theory is understood as a framework for predicting measurement outcomes, not for depicting what particles are doing when they are not being measured. Entanglement, from this standpoint, is not a mysterious connection waiting to be explained. It is simply a feature of the rules governing what can be said about outcomes. From this perspective, asking what entangled particles are doing between measurements is considered an ill-posed question. The theory, it is argued, does not provide that kind of description, and does not need to. What matters is that the predictions match experiments, which they do with extraordinary accuracy. Entanglement challenges intuition, because intuition evolved to deal with macroscopic objects, not quantum systems. Another family of interpretations takes a different approach. These interpretations accept the maths of quantum mechanics, but insist that it must correspond to some underlying physical reality, even if that reality is unfamiliar. In these views, entanglement reflects a genuine feature of the world, not merely a bookkeeping device for predictions. Some interpretations suggest that when particles become entangled, they remain part of a single physical system regardless of distance. The correlations are then not surprising, because the system was never truly divided in the first place. Separation in space does not imply separation in description. Entanglement simply reveals that spatial distance is not the only relevant organizing principle at the quantum level. Other interpretations propose that all possible outcomes of quantum measurements are realized, each in its own branch of reality. In this view, entanglement does not involve mysterious coordination across space. Instead, it reflects how different branches of the universe remain correlated due to a shared history. Each measurement outcome occurs, but observers experience only one branch. The correlations arise because the structure of branching preserves relationships established earlier. These ideas can sound extravagant when stated plainly, but it is important to note that they do not alter any experimental predictions. They reproduce exactly the same results as other interpretations. Their value lies not in testability, but in how they organize intuition. Another class of interpretations attempts to restore a more classical picture by introducing additional structure beneath quantum mechanics. These approaches often involve hidden variables or guiding mechanisms that determine outcomes while still reproducing quantum statistics. In such views, entanglement reflects coordinated behavior governed by deeper rules. However, as established by Bell's work and subsequent experiments, any interpretation that preserves both locality and predetermined outcomes faces serious constraints. Interpretations that introduce hidden variables must accept some departure from classical locality or independence. This does not make them impossible, but it shapes how they are formulated. What all of these interpretations share is an important feature. They agree on what will be observed. no matter which interpretation one adopts, calculations of entanglement experiments produce the same numerical predictions. Photons will display the same correlations. Measurement statistics will match. Technologies built on entanglement will function identically. This is why interpretations coexist rather than compete in the usual scientific sense. There is no experiment that can distinguish between them, at least not with current understanding. Choosing an interpretation is therefore not a matter of evidence, but of conceptual preference. For some physicists, this is unsettling. Science is often expected to deliver a single coherent picture of reality. Yet in quantum mechanics, multiple pictures coexist, all consistent with the same data. This situation is unusual, but not unique. Similar issues arise in other areas of physics, where different mathematical descriptions capture the same phenomena. Importantly, the lack of consensus has not slowed progress. Physics advances by refining predictions, developing new technologies, and testing new regimes, not by settling philosophical debates. Entanglement experiments continue to improve regardless of which interpretation a researcher finds most compelling. Interpretation affects how entanglement feels, not how it behaves. In one view, entanglement is a limitation on what can be said about reality. In another, it is a clue to a deeper structure. In another still, it reflects the unfolding of multiple outcomes. Each framing carries different intuitions, metaphors, and emotional reactions, but the laboratory results remain unchanged. This separation between explanation and prediction is a defining feature of modern quantum physics. It allows physicists with very different philosophical commitments to work side by side, using the same equations and tools. Agreement on outcomes matters more than agreement on meaning. There is also a practical reason for this tolerance. Interpretations do not usually generate new predictions. Without testable differences, there is no scientific mechanism to eliminate one in favor of another. Rather than forcing a choice, the field allows multiple viewpoints to coexist, each offering insight without claiming final authority. This situation does not imply confusion or failure. It reflects the limits of what current theories are designed to answer. Quantum mechanics excels at predicting what will happen when systems are prepared and measured. It is less explicit about what exists independently of those processes. Whether that is a limitation of the theory or a feature of reality itself remains open. Entanglement sits at the center of this ambiguity. It exposes the tension between classical ideas of separability and quantum descriptions based on relationships. Interpretations respond to this tension in different ways, but none remove it entirely. Physicists are generally comfortable working within this landscape. They recognize that understanding can be layered. One layer concerns calculation and prediction, where agreement is nearly universal. Another layer concerns interpretation, where diversity persists. Progress in one does not depend on resolving the other. In fact, the history of physics suggests that interpretation often evolves more slowly than theory. Concepts that once seemed paradoxical can later be absorbed into a broader framework, or replaced by new language that feels more natural. Whether this will happen for quantum entanglement remains to be seen. For now, the coexistence of interpretations serves as a reminder of humility. It shows that even with precise experiments and powerful maths, some aspects of understanding resist closure. This does not weaken science. It highlights its openness. Entanglement does not demand a single story about reality. It demands consistency with evidence. Within that boundary, multiple stories remain possible. The task of physics is not to choose the most comforting one, but to ensure that any story told respects what has been measured. With that in mind, attention can begin to widen. Interpretations shape how entanglement is conceptualized, but they do not alter its consequences. The next step is to consider what entanglement implies beyond foundational debates, in areas where theory meets application and where these strange correlations begin to matter in practical and conceptual ways beyond the laboratory. Entanglement does more than challenge ideas about particles and distance. It quietly reshapes how physicists think about information itself, not information as messages, words, or symbols, but information as something physical, something that can be stored, shared, and transformed by the laws of nature. In everyday life, information is usually imagined as something that travels. A sound moves through air, a signal moves along a wire, a message is sent from one place to another. Classical physics fits comfortably with this picture. Information is carried by physical systems, and it moves through space over time. Quantum entanglement complicates this story. Experiments show correlations between distant systems that cannot be explained by any exchange of signals at the time of measurement. Yet these correlations do not allow messages to be sent. Something is shared, but nothing is transmitted. This forces a more careful distinction between correlation and communication. Correlation describes a relationship between outcomes. Communication requires control. In entangled systems, outcomes are linked, but they are not chosen. An observer cannot decide which result will appear when measuring a particle. Because of this lack of control, entanglement cannot be used to encode or send information in the ordinary sense. The correlations are real, but they are not a channel. This distinction is central to how physicists talk about information. In physics, information is treated operationally. That means it is defined by what can be done with it. Can it be copied? Can it be transmitted? Can it be used to predict future outcomes? From this perspective, entanglement provides correlations without providing a usable signal. This insight helped resolve early confusion. At first glance, entanglement seems to imply instantaneous influence. One measurement appears to be linked to another across distance. But when analysed carefully, no new information is created at the moment of measurement. Each observer sees a random outcome. The correlation only becomes apparent when results are later compared using ordinary communication. In this sense, entanglement shifts when information becomes accessible, not how it travels. The information about the relationship between outcomes exists in the joint system, but it cannot be accessed locally. Only by bringing data together can the pattern be revealed. Until then, each measurement result looks unremarkable. This way of thinking led to the development of a new field known as quantum information science. Rather than asking what quantum systems are, this field asks what quantum systems can do with information. It treats entanglement not as a mystery to be explained away, but as a resource to be understood and used. One of the key insights of quantum information science is that information can be distributed across systems in ways that have no classical counterpart. In an entangled state, information about the system is not stored in either part alone. It is stored in the relationship between them. Remove one part and the information disappears. Only together does it exist. This idea is deeply counterintuitive, but it has precise consequences. It explains why entanglement cannot be copied. In classical information, copying is straightforward. A message can be duplicated without loss. In quantum systems, copying an unknown state is impossible. This is not a technical limitation. It is a fundamental rule arising from the structure of quantum mechanics. Entanglement also clarifies why measurement plays such a distinctive role. Measuring part of an entangled system does not reveal hidden information carried by that part alone. It reshapes the information content of the combined system. The act of measurement changes what can be known, not because information is destroyed, but because it is redistributed. Physicists often emphasize what entanglement does not allow, precisely because popular descriptions tend to exaggerate its power. Entanglement does not enable faster-than-light communication. It does not allow remote control of distant systems. It does not permit the extraction of unlimited information from a single particle. These limits are as important as the possibilities. At the same time, entanglement allows tasks that are otherwise impossible. Certain kinds of coordination can be achieved only if systems share entanglement. Certain forms of security become possible only because entanglement restricts what an eavesdropper can learn. These advantages arise not from sending information faster, but from how information is structured. This balance between constraint and capability is characteristic of quantum information. The rules are strict, but they open new possibilities precisely because they are strict. Entanglement does not remove limits. It replaces familiar limits with unfamiliar ones. Physicists describe information in this context using careful language. They speak of accessible information, mutual information, and correlations, always with reference to specific operations. Information is not an abstract substance floating through space. It is something that becomes available through interaction, measurement, and comparison. Seen this way, entanglement reveals that information is not always local. In classical systems, information about an object can be accessed by examining the object itself. In entangled systems, some information exists only globally. No local measurement can uncover it. This challenges the assumption that knowing the parts is enough to know the whole. This insight has influenced how physicists think about fundamental laws. It suggests that relationships may be just as fundamental as objects. The universe may store information not only in things, but in how things are connected. Entanglement makes this idea concrete and testable. There's also a practical reason this perspective matters. Technologies built on quantum principles rely on precise control of information. Understanding what entanglement allows and forbids is essential for designing reliable systems. Without a clear picture of information flow, such technologies would be impossible to scale or secure. Yet even here, restraint is important. Quantum information science does not promise unlimited power. It does not overturn thermodynamics or computation entirely. Instead, it refines what is possible within physical law. Entanglement expands the toolkit, but it does not remove the need for careful engineering and error correction. Throughout this discussion, one theme remains consistent. Entanglement reshapes how information is organized, not how fast it moves. The speed of light remains a fundamental limit. Causality remains intact. What changes is the architecture of correlations, the way information is distributed across systems rather than concentrated in individual parts. This architecture has consequences beyond technology. It feeds back into foundational questions about reality. If information is fundamentally relational, then descriptions based solely on local properties may always be incomplete. Entanglement becomes not just a feature of quantum mechanics, but a clue about how nature encodes structure. Importantly, none of these ideas require metaphysical speculation. They're grounded in operational definitions and experimental results. Physicists define information by what can be measured, transmitted, or inferred. Entanglement alters those possibilities in specific, testable ways. As understanding of quantum information deepened, entanglement moved from being a philosophical problem to being a practical resource. This shift did not diminish its conceptual importance, it sharpened it. By asking what entanglement allows in terms of information processing, physicists gained a clearer view of its role in the physical world. The discussion of information naturally leads toward application. Once entanglement is understood as a resource that structures information in non-classical ways, it becomes possible to ask how that resource can be harnessed. not to break the rules of physics but to work within them more creatively. This marks a transition in focus. Having explored what entanglement does to information, attention can now turn to how those altered information structures are used in real systems. The same correlations that once troubled intuition now form the basis of new technologies and experimental techniques, where the abstract ideas of quantum information take on concrete form. Entanglement moved into technology quietly, without grand announcements or sudden revolutions. Long before it appeared in headlines, it had already become part of how physicists think about building and controlling quantum systems. What once seemed like an abstract feature of theory gradually revealed itself as something that could be prepared, maintained, and used, at least in carefully controlled settings. One of the most discussed areas where entanglement plays a role is quantum computing. Unlike classical computers, which process information using bits that are either 0 or 1, quantum computers use quantum systems that can exist in combinations of possibilities. Entanglement allows these systems to share information in ways that classical bits cannot. When quantum components are entangled, the state of the whole system carries more structure than the sum of its parts. In practical terms, this means certain computational tasks can be approached differently. Entanglement enables correlations between quantum bits that allow some problems to be solved with fewer steps than any known classical method. Importantly, this does not mean quantum computers are faster at everything. Their advantages are highly specific and depend on carefully designed algorithms. Laboratory demonstrations of entangled quantum bits have been achieved using many physical platforms. These include superconducting circuits cooled to near absolute zero, trapped ions held in the electromagnetic fields, and photons guided through optical systems. Research groups across the world, from national laboratories to university-based teams, have shown that entanglement can be created and manipulated with increasing precision. However, it is crucial to distinguish these demonstrations from practical, large-scale machines. Maintaining entanglement is difficult. Quantum systems are extremely sensitive to their environment. Heat, vibration, stray fields, and imperfections in materials all threaten to disrupt entangled states. As systems grow larger, these challenges multiply. This is why progress in quantum computing has been steady rather than explosive. Each additional quantum component increases complexity. Engineers must balance isolation with control, stability with flexibility. Error correction techniques, which themselves rely on carefully structured entanglement, are essential just to keep systems functioning long enough to perform useful operations. Another area where entanglement has found practical use is quantum sensing. Here, entangled systems are used to make measurements with extraordinary precision. By linking particles together in specific ways, physicists can reduce certain kinds of noise that limit classical measurements. This allows extremely sensitive detection of quantities such as magnetic fields, time intervals, or gravitational effects. These techniques are already finding applications in research and industry. Atomic clocks that rely on quantum correlations provide timekeeping accuracy far beyond previous standards. Highly sensitive detectors are used in navigation, geology, and fundamental physics experiments. In these cases, entanglement enhances measurement without introducing exotic behavior. The devices operate reliably and predictably within well-understood limits. Quantum cryptography provides another example where entanglement has moved from concept to application. In these systems, entanglement is used to distribute encryption keys in a way that reveals any attempt at interception. The security does not depend on computational difficulty, but on physical law. Any disturbance introduced by an eavesdropper changes the correlations and can be detected. Practical quantum communication systems have been demonstrated over increasing distances, including links between ground stations and satellites. International collaborations have played a central role here, combining expertise in optics, engineering, and information theory. These efforts show how entanglement can be maintained and verified even outside laboratory conditions. Despite these successes, it is important to avoid exaggeration. Quantum cryptography does not make communication invulnerable in all respects. It addresses specific vulnerabilities while leaving others untouched. Secure systems still depend on careful implementation, trusted hardware, and sound protocols. Entanglement strengthens security, but it does not replace good engineering practice. Across all these technologies, one theme is consistent. Entanglement is powerful but fragile. Creating it is only part of the challenge. Preserving it long enough to be useful is often harder. Scaling systems while maintaining reliability remains one of the central engineering problems of the field. This is where realism becomes essential. Popular descriptions sometimes suggest that quantum technology will rapidly replace classical systems or solve all computational problems. Physicists working in the field are far more cautious. They understand both the promise and the limitations. Progress is measured in incremental improvements, not sweeping transformations. Research institutions play a crucial role in this steady advance. Large-scale facilities provide the infrastructure needed for precision experiments. Universities contribute theoretical insight and training. Industry partners help translate laboratory techniques into robust devices. Collaboration across borders is common, reflecting the shared challenges involved. International projects have demonstrated that progress depends on coordination as much as innovation. Standardizing components, sharing data, and cross-checking results all contribute to reliability. Entanglement-based technologies benefit from the same scientific culture that established quantum mechanics itself, one built on repetition and verification. It's also worth noting that many applications of entanglement remain experimental. Prototypes exist. Proofs of principle have been demonstrated. But deploying these systems widely requires solving problems of cost, durability, and integration with existing infrastructure. This process takes time. Engineers working on quantum devices often describe their work less in terms of breakthroughs and more in terms of refinement, improving coherence times, reducing error rates, enhancing fabrication techniques. These are not glamorous tasks, but they determine whether entanglement remains a laboratory curiosity or becomes a dependable tool. The gap between demonstration and deployment is especially clear in quantum computing. While small-scale processors exist, building machines with thousands or millions of reliable quantum components remains an open challenge. Entanglement must be generated and maintained across large systems without collapsing under noise. Achieving this requires advances in material science, control electronics, and theoretical design. This does not diminish the significance of current achievements, it places them in context. The history of technology shows that transformative tools often spend decades in development before reaching maturity. Quantum technology is following a similar path, guided by careful experimentation rather than hype. One of the reasons entanglement has proven useful is that it aligns naturally with the operational view of physics. It provides concrete advantages within well-defined constraints. It does not require abandoning existing physical laws. It works within them, exploiting features that were previously considered inconvenient or strange. At the same time, these technologies reinforce the lessons learned from foundational experiments. Entanglement enables coordination without communication. It enhances precision without enabling control at distance. It offers power, but only under strict rules. Each application reflects the same balance observed in laboratory tests. As quantum technologies mature, they continue to inform fundamental understanding. Practical challenges highlight which aspects of entanglement are robust and which are delicate. Engineering problems feed back into theory, refining models of decoherence and interaction. The boundary between foundational physics and applied science becomes increasingly blurred. This interplay between theory and technology is not accidental. It reflects the depth of entanglement as a concept. What began as a puzzling feature of equations now shapes how information is processed, measured, and secured. Yet it does so quietly, without overturning the broader structure of physics. The future of entanglement in technology will likely be defined by limits as much as by possibilities. Understanding where entanglement fails is just as important as understanding where it succeeds. These limits are not disappointments, they are guides. By acknowledging constraints and avoiding exaggerated expectations, physicists and engineers build systems that work. Entanglement becomes not a symbol of mystery, but a practical resource with clearly defined uses. With this perspective, attention naturally shifts toward what constrains entanglement in real systems. Noise, interaction with the environment, and scale all impose boundaries. Understanding those boundaries is essential for both technology and theory, and it sets the stage for examining the fundamental limits that entanglement cannot overcome, no matter how carefully it is used. Entanglement is often described as one of the most striking features of quantum mechanics, yet it is also one of the most fragile. Creating entangled systems in theory is straightforward. Maintaining them in the real world is not. The difference between these two facts lies at the heart of why entanglement remains challenging to use at large scales. In theory, quantum mechanics allows systems to remain entangled indefinitely. The mathematical description places no time limit on how long correlations can persist. As long as the system evolves according to the equations of the theory, the entangled relationship remains intact. Nothing in the formalism demands that entanglement fade or decay on its own. In practice, quantum systems are never perfectly isolated. They exist in an environment filled with stray influences. Tiny electromagnetic fields, thermal vibrations, collisions with surrounding particles, and imperfections in experimental apparatus all interact with quantum systems whether researchers want them to or not. These interactions are not dramatic. They are subtle, constant, and unavoidable. This is where decoherence enters the picture. Decoherence is the process by which a quantum system loses its distinctly quantum behavior through interaction with its surroundings. It does not require a measurement in the traditional sense. It occurs simply because the system becomes entangled with the environment itself. As this happens, the delicate correlations that define entanglement within the system are diluted and effectively lost. A helpful way to think about decoherence is to imagine trying to keep a whisper intact in a crowded room. The whisper does not disappear because someone shouts over it. It disappears because countless small sounds blend together, overwhelming the original signal. In a similar way, environmental interactions overwhelm the precise correlations that entanglement depends on. Importantly, decoherence does not destroy energy or violate physical laws. It redistributes information. The information that once described the entangled system becomes spread across the environment. Once this happens, it becomes inaccessible for practical purposes. Recovering it would require tracking every interaction with every surrounding particle, an impossible task. This sensitivity to environment is why entanglement is so difficult to maintain. Even minimal contact with the outside world can disrupt it. Temperature is a major factor. Thermal motion introduces random interactions that quickly degrade quantum states. This is why many quantum experiments are performed at extremely low temperatures, sometimes only fractions of a degree above absolute zero. Isolation presents another challenge. Shielding quantum systems from electromagnetic interference requires carefully designed enclosures and materials. Even then, perfect isolation is impossible. Engineers aim instead for isolation good enough that useful operations can be performed before decoherence takes over. Time also plays a role. Entangled states have a limited lifetime, known as coherence time. This is the window during which quantum correlations remain usable. For some systems, this window is extremely short, measured in tiny fractions of a second. For others, careful design can extend it significantly. Improving coherence time is one of the central goals of quantum engineering. The difficulty increases dramatically as systems grow larger. Entangling two particles is challenging but achievable. Entangling many particles at once multiplies the number of ways the environment can interfere. Each additional component introduces new paths for decoherence. The system becomes harder to control and easier to disrupt. This scaling problem explains why large-scale entanglement is so difficult to achieve. In theory, quantum mechanics allows enormous networks of entangled systems. In practice, maintaining coherence across such networks requires extraordinary control. Small imperfections that are negligible in simple setups become dominant at larger scales. Another source of fragility comes from control itself. Manipulating quantum systems requires interaction. Pulses of light, electromagnetic fields, and mechanical adjustments are used to prepare and measure states. Each interaction risks disturbing the system. Engineers must strike a careful balance between controlling a system and preserving its coherence. This tension highlights a fundamental difference between theory and practice. The equations of quantum mechanics assume idealized conditions. Real experiments must contend with imperfect materials, finite precision, and unavoidable noise. Bridging this gap requires ingenuity rather than new physics. Noise is not a single phenomenon. It comes in many forms. Random fluctuations in power supplies introduce electrical noise. Vibrations from nearby equipment introduce mechanical noise. Even cosmic radiation can occasionally affect sensitive systems. Each source may be weak on its own, but together they form a persistent background that quantum systems cannot ignore. Physicists characterize noise statistically, measuring how it affects systems over time. These measurements guide the design of experiments and devices. By understanding which noise sources dominate, engineers can prioritize improvements. Sometimes shielding helps, sometimes cooling helps, sometimes entirely new system designs are required. This realistic approach tempers expectations. Entanglement is not a magical state that persists regardless of circumstance. It is a condition that must be actively protected. This does not diminish its importance, it clarifies its nature. The contrast between theory and practice is especially clear when comparing simulations to experiments. On paper, entangled systems behave cleanly and predictably. In the laboratory, researchers spend much of their effort dealing with imperfections. Progress often comes not from new ideas, but from incremental reductions in noise and error. Despite these challenges, significant advances have been made. Improved materials reduce unwanted interactions. Better fabrication techniques produce more uniform components. Sophisticated error mitigation strategies help preserve coherence longer than previously possible. Each improvement extends the range of what can be done with entanglement. Still, there are limits. No system can be perfectly isolated. No environment can be completely eliminated. These constraints are not failures of technology. They are features of the physical world. Understanding these limits is essential for maintaining realism. Entanglement will not scale effortlessly to arbitrary sizes. It will not behave identically in all contexts. Recognizing this prevents disappointment and guides productive research. It also deepens understanding of quantum mechanics itself. Decoherence provides insight into why the macroscopic world appears classical. Large objects interact so strongly with their environments that quantum correlations are suppressed almost instantly. Entanglement exists, but it is spread so widely that it becomes invisible. In this sense, fragility is not a flaw. It is part of the explanation for why everyday objects do not display obvious quantum behavior. The same processes that make entanglement difficult to maintain also give rise to the stable, predictable world experienced at human scales. Researchers continue to explore ways to push against these boundaries. Techniques such as error correction use carefully structured entanglement to protect information from noise. These methods do not eliminate decoherence, but they manage it, extending coherence times and enabling more complex operations. Even these techniques face limits. Error correction requires additional resources, increasing system size and complexity. This again brings scaling challenges to the forefront. Each solution introduces new trade-offs. Throughout all of this, the distinction between theory and practice remains clear. Quantum mechanics provides a framework that allows entanglement. Engineering determines how far that allowance can be taken. The interplay between the two shapes the future of the field. By grounding discussion of entanglement in its constraints, physicists maintain a clear view of what is achievable. Progress is measured not by spectacular claims, but by improved stability, longer coherence, and better control. These achievements may be quiet, but they are profound. As systems grow in size and complexity, questions of scale become unavoidable. How does entanglement behave when extended across many components? What new limits appear? Which strategies remain effective? These questions naturally lead beyond individual systems toward networks, distances, and collective behavior. Understanding fragility is therefore not an endpoint. It is a transition. It sets the stage for examining how entanglement behaves as scale increases, and how far quantum correlations can be extended before the constraints of the physical world assert themselves once again. Entanglement often sounds most dramatic when distance enters the conversation. Two particles created together, then separated by vast stretches of space, still displaying correlations that refuse to fade. It is here, more than anywhere else, that intuition tends to protest. Distance feels like it should matter. Separation feels like it should weaken connection. And yet, experiments repeatedly show that distance itself does not behave the way everyday experience suggests. From the standpoint of quantum mechanics, this is not actually surprising. Entanglement is not something that travels from one place to another. It is established at the moment a joint system is created. Once that shared description exists, separating the components does not gradually erode the relationship. The correlations remain defined by the state of the system, not by the space between its parts. Laboratory experiments first demonstrated this over distances of a few meters, then across rooms, then between buildings. As techniques improved, researchers pushed farther. Optical fibers carried entangled photons across kilometers. Free space experiments sent particles across valleys and between mountain tops. Each increase in distance raised the same question. Would the correlations weaken, blur, or disappear? They did not. What did change with distance was not the entanglement itself, but the difficulty of preserving it. Longer distances introduce more opportunities for loss, noise, and environmental interaction. Photons can be absorbed or scattered. Timing becomes harder to control. Alignment becomes more delicate. These are practical challenges, not fundamental ones. When experiments succeed in delivering entangled particles intact, the correlations remain just as strong. This distinction is crucial. Distance does not degrade entanglement in principle. It complicates its preservation in practice. When an experiment fails at long range, it is because the system has been disturbed, not because space itself has diluted the quantum relationship. Some of the most striking demonstrations of long-distance entanglement have involved satellites. In these experiments, entangled photons are generated on Earth or in orbit, then sent to widely separated ground stations. The distances involved can span hundreds or even thousands of kilometers. From a human perspective, this is immense. From the perspective of the quantum state, it is irrelevant. Results from these experiments show the same pattern seen in laboratory tests. Measurement outcomes remain correlated in exactly the way quantum mechanics predicts. Bell inequality violations persist. No signal passes between stations faster than light. The correlations appear when data is later compared using ordinary communication. Using satellites introduces unique challenges. Atmospheric turbulence can distort light. Weather can interrupt transmission. Precise tracking is required to keep optical links aligned as satellites move rapidly across the sky. Overcoming these challenges requires sophisticated engineering and international collaboration. Institutions across the world have contributed to these efforts, combining expertise in optics, timing, navigation, and data analysis. These experiments are not quick demonstrations. They are carefully planned campaigns, often repeated many times to ensure reliability. Their success reflects not only quantum theory, but decades of technological development. What these long baseline experiments clarify is what distance does not do. It does not introduce delays into entanglement itself. It does not weaken correlations. It does not create opportunities for communication outside known physical limits. Distance changes logistics, not laws. Scale comparisons help make this clearer. Consider two clocks synchronized on Earth, then carried far apart. Their synchronization does not slowly decay simply because they are separated. What matters is whether something disturbs them. Entanglement behaves similarly. Once established, separation alone does not undo it. Of course, the analogy has limits. Entangled systems are not clocks, and their correlations are not classical synchronization. But the comparison helps shift attention away from space as an active agent. Space does not stretch or strain entanglement. It simply provides room for systems to exist apart. This understanding also helps avoid a common misconception. When entanglement spans large distances, it is tempting to imagine a hidden influence reaching across space. Experiments consistently rule this out. The correlations appear without any observable exchange at the moment of measurement. No matter how far apart the systems are, no controllable effect travels between them. This speed of light remains a firm boundary. Information about measurement outcomes still travels through conventional channels. Only after results are compared does the full pattern emerge. Until then, each observer sees random outcomes, indistinguishable from any other quantum measurement. Distance, then, does not grant entanglement new powers. It reveals its existing structure more starkly. The further apart systems are, the harder it becomes to imagine classical explanations. At the same time, the physical constraints become clearer. Nothing is gained in terms of signaling or control. As experiments have extended entanglement across larger distances, they have also highlighted the role of scale. Small systems are easier to isolate and protect. Larger systems face increasing interaction with their surroundings. Long-distance entanglement is therefore not limited by theory, but by engineering. This distinction between theoretical possibility and practical difficulty is a recurring theme. Quantum mechanics allows entanglement across arbitrary distances. The universe does not forbid it. But implementing it requires managing loss, noise, and timing with extreme precision. These challenges grow with scale. Understanding this prevents exaggeration. Entanglement does not imply that the universe is stitched together by instantaneous connections. It implies that certain relationships, once established, are indifferent to spatial separation. That is a subtler and more disciplined claim. It also reinforces why careful language matters. Physicists speak of non-classical correlations, not non-local forces. They speak of shared states, not invisible signals. This precision keeps discussion grounded in what experiments actually show. As distance increases, another question naturally arises. If entanglement can span such large scales, what does that imply about the structure of reality itself? Does space lose its fundamental role? Are relationships more basic than locations? Physicists approach these questions cautiously. The experiments themselves do not answer them directly. They show that spatial separation does not exhaust the description of a system. They do not say that space is irrelevant or illusory. They simply show that it is not the only organizing principle at work. Scale also invites humility. At human scales, quantum effects are almost always washed out by interaction with the environment. Entanglement exists everywhere in principle, but it becomes inaccessible almost instantly for large objects. The classical world emerges not because quantum mechanics stops applying, but because entanglement spreads too widely to observe. Long-distance experiments sit at an interesting boundary. They operate at scales where quantum effects remain visible, yet where classical intuition insists they should not. This tension is productive. It forces careful thinking without inviting speculation beyond evidence. As researchers continue to push entanglement across greater distances and more complex networks, they remain mindful of limits. Every experiment is designed to test what changes and what does not. So far, the message has been consistent. Distance complicates implementation, not principle. This consistency strengthens confidence in the theory. Quantum mechanics does not behave differently when systems are far apart. It behaves differently from classical expectation, but it does so reliably. That reliability is what allows entanglement to be treated as a physical feature rather than a philosophical curiosity. At the same time, the dramatic appearance of a long-distance entanglement encourages restraint. It is easy to overinterpret these results, to draw conclusions about instantaneous influence or deep metaphysical unity. The experiments themselves resist such readings. They reveal structure, not shortcuts. Recognizing this helps maintain balance. Entanglement across distance is remarkable, but it does not overturn the broader framework of physics. It fits within it, respecting established constraints while expanding understanding of how systems can be related. As scale increases, the need for careful interpretation becomes greater, not smaller. The farther intuition is stretched, the more tempting it becomes to replace explanation with metaphor. Physics advances by resisting that temptation. With entanglement now demonstrated across distances once thought unimaginable, the focus begins to shift again. The question is no longer whether distance matters, but how to think responsibly about what does and does not follow from these results. That shift invites a more reflective stance. The experiments have spoken clearly about correlation, constraint, and scale. What remains is to consider how much meaning can be safely extracted from them, and where caution is required when moving from measurement to interpretation. Entanglement attracts misunderstanding almost as reliably as it attracts attention. The idea that distant systems can share correlations that defy classical explanation is unusual enough that it invites metaphor, exaggeration, and creative reinterpretation. Over time, this has produced a long list of things entanglement is said to imply. Many of them are compelling. Most of them are wrong. Clarifying what entanglement does not mean is not an exercise in deflating curiosity. It is an essential part of understanding what the phenomenon actually is. Without clear boundaries, intuition drifts, an explanation quietly turns into speculation. One of the most persistent misconceptions is that entanglement involves communication. The image is familiar. A measurement here somehow sends information there, instantly and invisibly. This image is powerful, and it is also incorrect. Entanglement does not transmit messages. It does not carry signals. It does not allow influence to travel faster than light. Experiments show strong correlations, but they also show strict limits. The outcome of any individual measurement is unpredictable. No observer can choose the result they obtain. Because of this, no information can be encoded in the measurement itself. The correlation only becomes apparent when results are later compared using ordinary communication channels. This distinction between correlation and communication is central. Entanglement links outcomes, not actions. It aligns statistics, not intentions. Confusing the two leads to claims that sound exciting but have no basis in experiment. Another common misunderstanding links entanglement to consciousness. It is sometimes suggested that observation requires awareness, or that entanglement connects minds as well as particles. These ideas usually arise from a loose reading of the word observation. In physics, observation does not mean human awareness. It means interaction. A measurement occurs when a system interacts with another system in a way that produces a definite outcome. Detectors, photographic plates, electronic sensors, and even stray particles in the environment can serve this role. Consciousness plays no special part in the process. Entanglement appears and disappears regardless of whether anyone is watching. This point has been tested extensively. Experiments are run automatically. Data is collected and analysed long after measurements occur. The results do not depend on attention, intention, or awareness. Entanglement responds to physical interaction, not mental states. Closely related is the idea that entanglement implies a kind of universal unity, where everything is instantly connected to everything else in a meaningful way. While it is true that interactions can produce entanglement, and that entanglement can spread, this does not imply a permanent, all-encompassing connection. In realistic environments, entanglement is constantly being created and destroyed. Interactions with surroundings cause decoherence, rapidly dispersing correlations. At large scales, entanglement becomes inaccessible almost immediately. The classical world emerges precisely because these quantum relationships are overwhelmed by environmental interaction. This is why everyday objects do not display obvious entanglement effects. It is not because quantum mechanics stops applying. It is because the relevant correlations are washed out too quickly to observe. The universe is not quietly synchronized at all scales. It is noisy, interactive, and dynamic. Another misunderstanding concerns causality. Entanglement is sometimes described as allowing effects to occur without causes, or causes to act backward in time. This language arises from the surprise of seeing correlated outcomes without an obvious mechanism connecting them. In reality, causality remains intact. Each measurement outcome has a cause in the interaction between system and apparatus. What entanglement challenges is not causality itself, but the classical assumption that causes can always be described locally and independently. The correlations reflect shared preparation, not retroactive influence. No experiment has ever shown a violation of causal order. Events still occur in time. Signals still propagate at finite speeds. Entanglement respects these constraints completely. Metaphors often add to the confusion. Phrases like spooky action, invisible threads, or quantum magic are memorable, but they obscure more than they clarify. They suggest forces and influences that do not exist. Entanglement does not pull, push, whisper, or coordinate. It describes how probabilities are structured within a system. This does not mean metaphor should be avoided entirely. Metaphor can help build intuition, but it must be handled carefully. When metaphor replaces mechanism, understanding suffers. The goal is not to make entanglement feel mysterious, but to make it feel precise. Another claim sometimes encountered is that entanglement undermines reality itself, implying that nothing exists until it is observed. This interpretation goes beyond what experiments support. Quantum mechanics describes how measurement outcomes are predicted. It does not require denying the existence of an external world. Different interpretations of the theory offer different answers to questions about underlying reality, but none of them require abandoning the idea that something exists independently of observation. What they question is how properties should be described prior to measurement, not whether the world exists at all. It is also important to separate entanglement from randomness. Quantum outcomes are probabilistic, but entanglement is not simply randomness. It is structured randomness. The outcomes are unpredictable individually, but their relationships are tightly constrained. This combination of uncertainty and order is what makes entanglement distinctive. Misunderstanding this leads to the idea that anything can happen in quantum mechanics. In fact, quantum mechanics is highly restrictive. It forbids far more behaviors than it allows. Entanglement does not open the door to arbitrary outcomes. It imposes specific patterns that must be respected. Popular accounts sometimes suggest that entanglement can be used to explain unexplained phenomena in psychology, biology, or everyday experience. These claims almost always rest on misunderstanding scale. Quantum effects dominate at microscopic levels. At macroscopic scales, environmental interaction suppresses them almost instantly. This does not mean quantum mechanics is irrelevant to biology or chemistry. It plays a role in molecular interactions and energy transfer. But invoking entanglement to explain consciousness, intention, or coincidence stretches the concept beyond its domain. Physicists are careful about this boundary not out of defensiveness, but out of respect for evidence. Expanding a concept beyond where it applies does not deepen understanding, it blurs it. Clarifying what entanglement does not mean also protects the credibility of what it does mean. Entanglement is remarkable without embellishment. It challenges classical ideas of separability. It reshapes how information is understood. It enables new technologies within strict limits. None of this requires exaggeration. Helping intuition recalibrate is part of the process. Classical intuition evolved in a world where objects are large, warm, and constantly interacting. Quantum behavior emerges in regimes far removed from those conditions. Expecting intuition to transfer unchanged leads to confusion. Good explanations do not aim to shock. They aim to orient. They acknowledge surprise without feeding it. They replace dramatic claims with careful distinctions. Entanglement does not tell us that the universe is conscious. It does not reveal hidden messages beneath reality. It does not dissolve causality or allow communication without channels. It does not make everything the same or everything connected in a practical sense. What it does tell us is more subtle. It tells us that some physical descriptions must refer to relationships rather than isolated parts. It tells us that classical assumptions about independence have limits. It tells us that information can be distributed in ways that defy everyday expectations. Separating these grounded insights from metaphor protects both science and curiosity. It allows the phenomenon to remain strange without becoming vague. It keeps wonder anchored to evidence. As misconceptions are stripped away, what remains is a clearer view of entanglement's role in physics. Not as a universal explanation, but as a specific, testable feature of how certain systems behave. This clarity does not diminish its importance, it sharpens it. With boundaries drawn and misunderstandings addressed, the picture becomes more coherent. Entanglement can be placed alongside other physical principles, understood in terms of what it allows and what it forbids. This sets the stage for synthesis. Having explored theory, experiment, interpretation, application, and limitation, it becomes possible to step back and ask how these pieces fit together. What kind of understanding emerges when entanglement is seen not as an isolated curiosity, but as part of a broader, disciplined picture of the physical world? Entanglement can feel like a dramatic outlier when encountered in isolation, a strange rule tucked away in the corner of quantum mechanics. But when placed back into the wider structure of modern physics, it becomes something quieter and more integrated. It is not an exception to physical law. It is a natural consequence of how those laws are written and how they interact with one another. Modern physics is built from layers. At large scales, classical mechanics and relativity describe motion, gravity, and space-time with extraordinary accuracy. At smaller scales, quantum mechanics governs the behavior of particles, fields, and interactions. These layers do not contradict one another. They apply in different regimes, overlapping smoothly rather than colliding. Entanglement lives comfortably within this layered structure. It arises whenever quantum systems interact and then separate, which is not a special circumstance. Interactions are the foundation of physics. Forces, collisions, emissions, and absorptions all involve interaction. Entanglement is simply one of the ways quantum theory keeps track of what interaction leaves behind. Seen this way, entanglement is not an added feature bolted onto quantum mechanics. It is built into the core description of how systems combine. When quantum systems interact, the mathematics does not permit a clean separation into independent parts unless very specific conditions are met. Entanglement is the default outcome, not an anomaly. This perspective becomes clearer when entanglement is viewed through the lens of quantum field theory. In this framework, particles are not treated as isolated objects moving through empty space. They are treated as excitations of underlying fields that extend throughout space-time. Interactions occur locally, but the fields themselves are continuous and pervasive. Within quantum field theory, entanglement emerges naturally from how fields interact and exchange energy. When particles are created together or interact through a shared field, the resulting state reflects that shared history. The correlations encoded in entanglement are a record of interaction, not a mysterious add-on. This helps explain why entanglement respects locality, even while challenging classical intuition. Interactions occur at specific points in space-time. Nothing jumps across space. The correlations appear later because the systems carry a shared description forward in time. The structure of space-time remains intact. What changes is how information about the system is distributed. Entanglement also fits naturally alongside other foundational principles. Conservation laws, for example, play an important role. When two particles are produced together, conservation of energy, momentum, or other quantities can link their properties. In quantum mechanics, these links are expressed through entanglement rather than fixed values. The principle remains, the expression changes. The same is true for symmetry. Modern physics relies heavily on symmetry principles to determine which interactions are allowed. These symmetries shape the structure of quantum states, including entangled ones. Entanglement does not break symmetry. It reflects it. Placing entanglement within this broader context helps dispel the idea that it stands apart from the rest of physics. It does not undermine established theories, it extends them. The same mathematical framework that predicts entanglement also predicts atomic structure, chemical behavior, and the stability of matter. These successes are not separate achievements. They are manifestations of a single coherent description. This coherence is part of why physicists are comfortable with entanglement despite its counterintuitive nature. It does not require rewriting physical law. It requires learning to read those laws differently. What once seemed like an uncomfortable implication becomes an expected feature once the full structure is taken into account. Entanglement also plays a role in unifying different areas of physics. It connects questions about information, measurement, and interaction that once seemed distinct. Techniques developed to study entanglement inform research in condensed matter physics, particle physics, and cosmology. Concepts travel between fields, enriching each in turn. In condensed matter systems, for example, entanglement helps describe collective behavior in materials. Properties of solids, superconductors, and exotic faces of matter can be understood in terms of how large numbers of particles share quantum correlations. Here, entanglement is not a curiosity. It is a practical tool for understanding complex systems. In high-energy physics, entanglement has become a way to probe deep questions about space-time and gravity. While these connections remain an active area of research, they illustrate how entanglement serves as a bridge between seemingly distant domains. It links the quantum description of matter to broader questions about structure and geometry. What makes these connections possible is the cumulative nature of physics. New concepts rarely replace old ones entirely. They refine, extend, and reorganize understanding. Entanglement did not discard classical physics. It clarified the conditions under which classical descriptions apply. This cumulative view also explains why entanglement does not disrupt everyday experience. At macroscopic scales, interactions with the environment suppress observable quantum correlations almost instantly. Classical behavior emerges naturally from quantum rules under realistic conditions. The layers of physics align rather than conflict. Understanding this helps maintain balance. Entanglement is fundamental, but it is not omnipresent in a way that overrides other principles. It operates within constraints set by scale, interaction, and environment. Recognizing those constraints prevents overstatement while preserving significance. Physicists often emphasize integration rather than isolation for this reason. Entanglement is one thread in a larger tapestry. It weaves through theories of matter, energy, and information without tearing the fabric. Each time it appears, it does so according to the same underlying rules. This integrated perspective also reinforces why physics progresses even when some questions remain open. Entanglement raises deep issues about interpretation, but those issues do not block calculation, prediction, or application. Research advances by building on what is known while remaining open about what is not. The ability to work productively without complete philosophical closure is not a weakness. It is a strength. Physics has always advanced by refining models, testing limits, and expanding scope. Entanglement fits naturally into this tradition. Seen from this angle, the story of entanglement becomes less about disruption and more about continuity. It reflects the same pattern seen throughout the history of science. New ideas challenge intuition, are tested rigorously, and eventually find their place within a broader framework. This does not mean entanglement has been fully absorbed or rendered mundane. It continues to inspire research and provoke questions, but it does so from within physics, not from its edges. Integrating entanglement into physics as a whole allows it to be appreciated for what it truly is, a precise testable feature of quantum theory that connects interaction, information, and structure, not a bolt from the blue, but a consequence of how the world is described at its most fundamental level. As this integration deepens, the emphasis shifts away from surprise and toward perspective. Entanglement becomes one example of a broader lesson. That nature often resists simple categories, that relationships matter alongside objects. That understanding grows by adjusting intuition rather than abandoning it. With this perspective in place, the journey approaches its final phase. The pieces have been laid out. Theory, experiment, application, limitation, and integration now form a coherent picture. What remains is not another concept to introduce, but a moment to reflect on what this picture suggests about understanding itself, and about how physics accommodates ideas that initially seem to stretch the imagination beyond its comfort zone. Entanglement leaves an unusual impression once the details settle. It does not overthrow physics, and it does not replace one mystery with another. Instead, it quietly changes what feels natural. The equations continue to work. Experiments continue to agree. Technologies continue to function. What shifts is expectation. Physics has faced moments like this before. The idea that Earth moves around the Sun once felt deeply wrong. The notion that time flows differently depending on motion and gravity was once unthinkable. In each case, the world did not change. Human intuition did. Entanglement belongs to that same category. It asks for adjustment, not alarm. At first glance, entanglement appears to threaten the idea of an ordered universe. Correlations appear without visible causes. Outcomes line up without exchange. Distance seems less relevant than expected. These features can feel destabilizing if order is equated with familiarity. But order in physics has never depended on comfort. It depends on consistency. Entanglement is consistent. Its behavior follows precise rules. It appears under specific conditions and disappears under others. It does not behave differently from one experiment to the next. Its correlations can be predicted, tested, and used. Strangeness does not imply unreliability. In fact, some of the most reliable features of nature are also the most counterintuitive. One of the quiet lessons of entanglement is that understanding does not require visualization. Classical intuition relies heavily on pictures, objects moving through space, forces acting across distance, causes producing effects. Quantum mechanics does not always offer pictures that align with this instinct. It offers structure instead. Physicists do not need to imagine invisible threads or instantaneous influence to work with entanglement. They rely on mathematical relationships that encode how outcomes relate. These relationships can be checked against measurement. When they match, confidence grows, even if imagination lags behind. This separation between intuition and reliability is not a flaw. It is a feature of mature science. The more deeply physics probes reality, the less it resembles everyday experience. Atoms do not behave like miniature planets. Light does not behave like a stream of tiny balls. Time does not behave like a universal clock. Entanglement joins this list not as an exception, but as a continuation. Living with this kind of reality means accepting that explanation comes in layers. One layer tells what will happen. Another suggests why it happens. A third attempts to connect those explanations to broader ideas about reality. These layers do not always align perfectly. Physics remains effective even when interpretation remains open. Entanglement highlights this coexistence clearly. The predictions are sharp. The interpretations are varied. The experiments are decisive. The philosophical implications remain debated. None of this prevents progress. None of it undermines confidence in the theory's practical power. This is not resignation. It is a recognition of how knowledge grows. Science does not demand final answers before moving forward. It builds reliable structures first, then reflects on meaning over time. Entanglement has already earned its place in the structure. There is also a quieter reassurance embedded in entanglement. Despite its unfamiliar features, it does not introduce chaos. The universe remains orderly. Causality holds, energy is conserved, Signals respect limits. Nothing about entanglement allows the world to unravel into unpredictability. Instead, it reveals a subtler order, one based on relationships rather than isolated properties, one where systems carry information about their shared past, one where separation in space does not erase connection in description. This kind of order does not announce itself loudly. It is not dramatic. It is persistent. It shows up every time an experiment is repeated. It holds across distance, scale, and method. Reliability of this kind is the deepest form of reassurance physics offers. Living with non-intuitive reality also involves letting go of the need for resolution. There is a temptation to believe that every scientific question must end with a single satisfying picture. History suggests otherwise. Many of the most successful theories coexist with unresolved interpretive questions. Electromagnetism worked long before the nature of fields was fully understood. Thermodynamics functioned before atoms were confirmed. Quantum mechanics continues to work even as its interpretations multiply. Entanglement sits comfortably in this tradition. Incomplete understanding does not mean incomplete science. It means that the boundary between what is known and what is interpreted remains visible. That boundary is not a weakness. It is an honest map of where evidence ends and reflection begins. For many, the discomfort of entanglement fades with familiarity. The idea stops feeling like a challenge and starts feeling like background structure. Just as relativity quietly shapes navigation systems and timekeeping, entanglement quietly shapes how quantum systems are understood and used. This normalization does not dull curiosity, it redirects it. Once the shock subsides, attention shifts from whether entanglement is strange to what it can illuminate. How does it shape collective behavior? How does it limit information flow? How does it interact with space-time? These questions are constructive rather than reactive. Calm acceptance does not mean indifference. It means trusting the process that brought understanding this far. Entanglement was once a theoretical oddity. It became an experimental challenge. It became a technological resource. It is now an integrated principle. That arc is characteristic of physics. Ideas begin as unsettling. They become testable. They become reliable. Eventually they become ordinary, not because they are simple, but because they are understood within context. Entanglement also offers a subtle lesson about humility. It reminds us that intuition is shaped by scale and experience, not by fundamental truth. The universe is under no obligation to align with human expectations. Physics progresses by refining expectations, not by insisting on them. This humility does not weaken confidence, it strengthens it. When theories continue to work despite stretching intuition, trust grows. The success of entanglement-based predictions across decades of testing earns a kind of quiet authority. There is also comfort in the restraint entanglement imposes. It allows surprising correlations but forbids communication without channels. It permits non-classical relationships but preserves causal structure. It expands possibility while enforcing limits. That balance is characteristic of a stable theory, not a disruptive one. Seen this way, entanglement is less a rupture and more a reminder that reality can be orderly without being familiar, that explanation can be precise without being visual, that science can move forward without waiting for philosophical closure. Living with non-intuitive reality becomes easier when this pattern is recognized. Physics does not demand belief in paradox, it demands attention to evidence. When evidence accumulates, intuition adapts. Entanglement does not ask anyone to abandon common sense in daily life. Tables remain solid, signals remain finite, causes precede effects. The quantum world does not intrude where it does not apply. It remains layered beneath experience, shaping it without disrupting it. This layered view is perhaps the most calming takeaway. The universe accommodates many descriptions at once, each valid within its domain. Classical intuition governs everyday life. Quantum mechanics governs microscopic systems. Entanglement governs relationships between quantum systems. Each has its place. There is no need to resolve entanglement into something familiar. Familiarity is not the measure of truth. Reliability is, and by that measure, entanglement has earned its position. As this exploration draws toward its close, the emphasis shifts from explanation to perspective. Entanglement is no longer a question demanding an answer. It is a feature to live alongside. It shapes understanding without demanding finality. The universe does not insist on being intuitive. It insists on being consistent. Physics meets that insistence by adjusting language, refining models, and accepting limits where they exist. Entanglement fits within that approach naturally. It challenges, but it does not threaten. It surprises, but it does not destabilize. It invites thought, but it does not require resolution. Living with non-intuitive reality, then, is not a burden. It is the ordinary condition of doing physics at depth. Entanglement simply makes that condition visible. With this perspective in place, the remaining task is not to solve entanglement, but to situate it, to see it as one thread in a larger ordered fabric, a fabric that continues to hold even as understanding stretches. That quiet stability, more than any dramatic implication, is what entanglement ultimately reveals about the universe. Quantum entanglement began this journey as something unsettling, a feature of physics that seemed to resist common sense. By now, it no longer needs that framing. It does not stand apart as an exception or an anomaly. It sits comfortably within the structure of modern science, tested, refined, and understood well enough to be trusted, even if not fully resolved. What entanglement shows most clearly is not that the universe is chaotic or unknowable, but that it is organized in ways that do not always match everyday intuition. The world at its smallest scales does not divide neatly into independent pieces. Relationships matter. Shared histories matter. Descriptions sometimes belong to systems rather than to parts. None of this undermines order. It reveals a different kind of order, one that remains consistent across experiment after experiment. Throughout physics, this pattern repeats. Familiar ideas give way to more accurate ones. Certainty is replaced with precision. Visual comfort yields to mathematical reliability. Entanglement follows this path closely. It did not overthrow established science. It sharpened it. It exposed assumptions that had gone unquestioned and showed where they no longer applied. Importantly, entanglement did not weaken confidence in physics, it strengthened it. The theory predicted correlations that seemed implausible. Experiments tested them carefully. The results matched. Over time, repetition replaced surprise. Reliability replaced doubt. This is how trust is built in science, not through dramatic claims, but through consistency. Understanding in this context does not require final answers. Physics has never waited for philosophical closure before moving forward. It advances by building models that work, refining them when needed, and remaining honest about what remains open. Entanglement fits naturally into this approach. It is understood operationally, used practically, and interpreted cautiously. There is a temptation to treat unresolved questions as failures. Entanglement shows why that temptation should be resisted. The lack of a single agreed interpretation has not slowed progress. Calculations remain precise. Experiments remain decisive. Technologies continue to develop. The absence of consensus about meaning does not imply uncertainty about behavior. This distinction is essential. Nature does not demand that it be comfortable. It demands that it be consistent. Entanglement meets that demand fully. Its effects appear under specific conditions, disappear under others, and respect known constraints. It does not allow communication without channels. It does not violate causality. It does not introduce instability into the physical world. Instead, it reveals how the world maintains coherence, even when intuition struggles. The same laws that govern particles and fields also govern entanglement. The same principles of conservation, locality of interaction, and statistical structure apply. What changes is not the reliability of physics, but the expectations brought to it. This perspective allows entanglement to be placed where it belongs, not as a mystery demanding resolution, but as a feature to be understood in context. It informs how information is distributed. It shapes how systems interact. It enables technologies within clear limits. It integrates smoothly with broader physical theory. Seen this way, entanglement becomes less dramatic and more instructive. It shows how scientific knowledge grows by adjusting intuition rather than defending it. It shows how careful experimentation can resolve deep questions without answering every philosophical concern. It shows how trust in method can coexist with openness about interpretation. There is also reassurance here. Despite its unfamiliar features, entanglement does not suggest that reality is fragile or unpredictable. The universe remains stable, causes still precede effects. Measurements still produce consistent results. Even the most counterintuitive phenomena obey disciplined rules. This stability is what allows science to function. It is what allows theories to be tested and technologies to be built. Entanglement contributes to that stability by revealing structure, not by undermining it. The correlations it describes are precise, repeatable, and bounded. They add nuance without eroding foundations. For listeners encountering these ideas, it can be tempting to look for a moment of resolution, a final insight that makes everything feel intuitive again. Physics does not always offer that. Sometimes it offers something quieter, an understanding that works, even if it does not settle every question. That kind of understanding is not a compromise, it is the norm. Much of science operates in this space, confident in prediction, careful in interpretation, and patient with unanswered questions. Entanglement exemplifies this balance. The lesson is not that reality is beyond comprehension. It is that comprehension comes in degrees. Some aspects can be calculated precisely. Others can be described conceptually. Some remain open to interpretation. Together, they form a picture that is usable, coherent, and trustworthy. Entanglement does not require belief in paradox. It requires attention to evidence. It asks for discipline rather than awe. When approached this way, it becomes less unsettling and more instructive, a guide to how physics handles complexity without confusion. As this exploration concludes, there is no need to force wonder or urgency. Entanglement does not demand excitement. It rewards calm attention. It sits quietly within an ordered universe, doing what it always does, whether it is noticed or not. The universe does not rush toward explanation, and neither must understanding. Entanglement remains what it has always been, a reliable feature of the natural world, patiently described by theory, confirmed by experiment, and integrated into a broader framework that continues to hold. Leaving this topic does not mean leaving uncertainty behind. It means recognizing that uncertainty and stability can coexist. That knowledge can be incomplete and still trustworthy. That physics can be both humbling and dependable at the same time. In that balance, entanglement finds its place, not as a riddle to be solved, but as a fact to live alongside. One that quietly reminds us that the universe is consistent, even when it is not intuitive, and that understanding is something that deepens over time rather than arriving all at once. With that perspective, there is nothing urgent left to resolve, only a broader view to carry forward, one in which entanglement is no longer strange or threatening, but simply part of how the world works.